Hello guys, before proceeding any further, let us have a quick review of what we considered in our previous discussion. This could be the first time some of you are looking into a problem in this perspective. So I just want to rather have a dedicated session wherein we highlight or we focus on the highlights of our previous session. So of course, if you are all too familiar with it, please go ahead and skip this session. So basically what we want to understand was, given our problem, was that we want to see the charging rate of our phone. To put it even more simply, we want to consider the fast charging aspect of our mobile phone. We took that view of our problem, we translated it and we placed it in the mathematical framework. So we are interested in understanding the fast charging aspect, and when we place it in the mathematical framework, it appears something like this, where C is the charge. So what we are essentially interested in when we talk about the fast charging, we want to see how the charge of the phone increases or decreases with respect to time. So with fast charging, how it increases with respect to time. Now this is our problem. We translated it and we placed it in the mathematical framework in this way. Now we introduced our material understanding of what happens during charging, and we rewrote this expression or rewrote this term as something like this. Our understanding of what happens during charging, what happens to a battery, the materialistic understanding of what happens to a battery during charging allowed us to change this expression, this term to this term here. Now when we change this term, even though it is the material understanding that allows us to change this expression to this expression, we have ignored or we have overlooked several other factors. Now we have a term that is something that we can mathematically handle. We started off with a problem, we translated it into something that we can now mathematically handle in a much easier manner. And this was allowed because we were able to understand what happens in the material framework of our battery. Now, the further material understanding allowed us to relate this to this. So essentially what we said was the charge of the battery depends on number of ions that is present in one of the electrodes. And further material understanding allowed us to arrive at this relation here, which states when we want to have a charging and the energy of the entire system needs to be rather minimal, this condition needs to be satisfied, that is the change in the number of ion in a particular electrode is proportional to the number of same ions present in the already existing in that electrode. So this relation we were able to arrive at based on our further understanding of what is happening to that of the system. Initially we have an expression, and that expression, from that expression now we are able to arrive at a relation. Both these are primarily from our understanding of the material and the physics of the material. Now we introduced the constants here and we expressed it in a solvable manner. The understanding that was translated to that of a mathematical equation now is being expressed in a solvable manner, wherein this constant here is the proportionality constant. And now we use the mathematical technique, something that we are familiar with, something that we saw in our previous discussion, to solve this and arrive at an expression that tells us or that can help us predict what would be the charge of my given gadget at a given time t. So time t is my time here, t is my time here. Now Ni is the number of ion that is present in the electrode, and depending on the number of ion, if it increases, my charge increases, if it decreases, my charge decreases. Now when I have an expression that talks about, that predicts the number of ions, I essentially will be able to relate it to my charge. So now I have an expression that helps me determine what will be the charge of my gadget at a given time t, and this is based on number of ions that is present in a given electrode at a given time t. So we started off with a problem, we translated it and placed that problem into a mathematical framework. Then we took our understanding of the material and arrived at an expression in equation for it, and only then we used our mathematical tool to solve it. This is where we used our mathematical tool to solve it. And all this primarily depends on our material understanding. So this is rather one of the framework, or largely one framework that we can use to adopt or theoretically approach any material based problem that is hugely relevant to us. Now, once we have arrived at this expression here, it is vital for us to understand what each of these parameters are. Mathematically speaking, these parameters could be expressed as a constants that we introduced while we are solving this expression. But since every other term has a physical significance, these two parameters should also have a physical significance. And we saw in our previous discussion that the first term here, it talks about the initial condition. That is, at my initial stage, what is the number of ion that is present? To put it simply, when I am charging my phone, what is the initial charge? Maybe 1%, 2%, 10%, or let's say you are so cautious that you start charging at 30% nonetheless. So that is the initial charge of your phone, the initial concentration of the ion that contributes to the charge of the phone. And this is a material constant. How much? The change in your charge relates to the initial charge, relates to the particular charge at that moment of the phone. So you have two parameters that you introduce during solving, and each of these parameters should have physical significance, and that needs to be realized. So in addition to this framework, it is also vital that each and every parameter that we have at the end of your expression, after you develop a model and you have an expression at the end of it, we need to be absolutely sure what these parameters mean. Now, just to give you a visualize, just to help you visualize what the impact of these different parameters are, here is rather a graph that would capture or that would help you realize what is the influence of each of these parameters. So essentially, when we talked about the solving the equation, that is how the number of ions in a given electrode is going to change, can be expressed as something like this. Now we have four different curves here, and in each of these curves, A0, that is the initial condition, has been changed. The initial conditions has been changed, and as you can see, when we change the initial condition, there is a significant difference in the rate of charging of your phone. Now, of course, we can use several sophisticated tools to plot this, but in this case, since for many of you this might be the first time you are coming across such equations in derivation, considering those, I have plotted just this using Google. All that I did was plot, I gave this, and the Google was able to give this to me. Wonderful. So all you can just try it for yourself. All you need to do is plot these things and you will be able to see different curves. Now this here, in the x-axis I have my time t, and in my y-axis I have my NT or NIT, that is rather the number of ions in my electrode that essentially translates to my charge. Now if I assume that this line here indicates my complete charge or my full charge, if this line here is my full charge, as you can see, depending on the initial condition, the time required to reach full charge significantly varies. So as you can see here, this initial condition requires this amount of time, 6. This initial condition here requires this amount of time. This initial condition, so initial conditions are 10, 20, 30, 100, and depending on the initial conditions, as you can see, the time taken to reach the full charge varies. So what we basically have is, we have an expression, and in addition to the trend, depending on the initial conditions as well, the time taken to reach full charge, the trend of it remains the same, is based on the expression, but the time taken, the specifics of it depend on the initial conditions. So this again depends on how many ions are there at the initial state when you place your phone in charging. Now there is also another parameter, that is the material constant. Again, we write our expression as something like this, the expression that governs our fast charging as this, and this we saw as our initial condition, and this is our material constant. So as in our previous plot, in this plot, each of these curves, they indicate different initial conditions, and in this case, each of these curves, they indicate different materials. Each of these curves, they indicate different materials. Now if I assume that this is my full charge depending on the material, the time taken. This is my time and this is my Ni, and the time taken to reach full charge, as you can see, noticeably varies. So each of these curves, they indicate as individual material, and if green indicates A, B, C and D, A reaches or attains the full charge first, and so on and so forth. So essentially this is how, when I consider different material constant, even though the trend remains the same, quantitatively the time taken to reach full charge significantly varies. So these are the significance of the two different parameters that gets introduced while solving the numerical expression, and both these play a critical role in determining what is the charge of my phone at a given time t. Alright, and these one of these depends on the material, the other depends on the initial conditions. Now, before winding up this discussion, it is vital to note that this is rather a toy model, meaning even though this has an essential aspects of an actual model, even though there is a framework that is usually adopted while, or that is often adopted while developing a mathematical model, this is again a toy model. Even though it resembles an actual car, it is not a real one. Even though it is impressive, you are able to understand it, you cannot say let me take it on an highway and go for a ride, because in real life situation there will be several other parameters, and more parameters you have, the more aspects you need to consider, the model becomes even more complicated or rather convoluted. So essentially you need to understand that this approach, whatever we have discussed in the context of batteries, even though the framework of it, the approach of it is rather valid, the model in itself, the expression, the equations we had, all this, they are rather a simplistic, a representation of what happens in the real world, and that's the reason we refer to these as a toy model. Of course, we can play with it, we can make ourselves comfortable with it, but very rarely you use it in a highway. Now, this doesn't mean that the entire approach that we have taken, the equation that we have solved, is rather restrictive, because there is a real life example wherein the same relation holds true. That is, the change in a given parameter is proportional to that of the parameter at a given time. So this expression or this relation holds true in one real life application, and that is nuclear power. Now in our present day and age, the alternate energy is something that every agency is funding and every researcher is keen to look into. Now, in this context, it is vital to note that when you consider nuclear power generation, we generate something called as a nuclear waste. And this nuclear waste is rather radioactive, and we want this nuclear waste to change from something that is radioactive to that of the non-radioactive. So we use a radioactive isotope to for this in this nuclear power plant to generate energy, and it also consequently generates waste, and this generated waste is also radioactive in nature, and we want to safeguard this radioactive waste in such a way that, and for a prolonged period of time or for a period of time, such that this waste, this radioactive waste, changes to that of a non-radioactive one, so that it is safe for us to dispose. And before it changes to the non-radioactive one, we cannot easily get rid of it, so we have to take a special care for it. So in order to understand how long will it take for the nuclear waste to turn from something radioactive to non-radioactive, people are interested in calculating, researchers are interested in calculating how long will it take for that to happen. And this is something called as a radioactive decay. This translation of pardon me, I forgot how to spell. So yeah, this translation of a radioactive waste to that of a non-radioactive substance is what we refer to as the radioactive decay. And the rate of this radioactive decay is proportional to that of the amount of radioactive content that is present. So dN by dt is now the rate of the radioactive decay. Rate of radioactive decay. And this rate of radioactive decay, that is what we mean by dN by dt, is proportional to the amount of radioactive substance that is present. Now, we have seen the approach how we can solve this expression and arrive at a solution for something like this, wherein you will be able to calculate the amount of the radioactive substances at a given time t. How we will be able to relate the amount of radioactive substances as a given time t. Now once we are able to plug in the real life parameters, we can safely say at this time t, we will be able to, or all that will be left in the radioactive waste will be negligible. So it will be negligible. So this estimation is possible because we have a theory or a material based understanding of this relation here. So even though what we considered was rather a toy model, the same approach is currently being used to understand how long should I have to store my radioactive waste, and how long or at what time will my radioactive waste or the radioactive substance in my radioactive waste becomes negligible. So even though what we have considered the framework is rather primarily is to develop the toy model, it is not exclusively for it. So this understanding you can also use to develop a model that is hugely relevant to us. So with this, we will wind up this discussion on developing a toy model. In the next session, we will rather consider one aspect that we introduced when we developed this model. We talked about placing a gun and using it in a next scene. So we talked about overlooking certain facts. What allows us to do it is something that we will get to in the next session. Goodbye.